Your most reliable clock can become a liar. In the deepest wells of gravity, a single hour for you could stretch into years for someone else. This is not science fiction. It is the profound reality of Einstein's universe, where mass warps the very fabric of time. By the end of this journey, you will understand how the cosmos itself controls the speed of time. We will travel to the edge of a black hole, where time appears to freeze for all eternity, and descend to the surface of a star so dense it bends light and slows seconds. Why does time run slower in these extreme places, and what does that reveal about the true nature of reality? What would you see if you watched a clock fall into the abyss? That clock on the mountain peak is not a fantasy. It is a real experiment conducted with astonishing precision. Scientists placed incredibly accurate atomic clocks at different altitudes, one high in the mountains and one at sea level. After accounting for every other possible factor, they found a definitive, measurable difference. The higher clock, experiencing slightly weaker gravity, ticked faster. Over years, it gained a tiny fraction of a second compared to its twin below. This minute gap is a monumental confirmation. It proves that time itself is malleable, bending to the will of mass and gravity. This is the heart of Albert Einstein's theory of general relativity, which completely reshaped our understanding of the universe. Before Einstein, gravity was seen as a simple, attractive force between objects. But Einstein proposed something far more profound. He suggested that gravity is not a force pulling through space, but rather the result of mass and energy warping the very fabric of the cosmos, a four-dimensional mesh we call spacetime. Think of spacetime as a vast, taut trampoline mat. Place a bowling ball in the center, and it creates a deep, curved depression. Now roll a marble across the mat. It will not travel in a straight line. Instead, it will curve inward, following the contour created by the bowling ball. The marble is not being pulled by a mysterious force. It is simply following the shortest path along the curved surface. In this analogy, the bowling ball is a planet or a star, and the marble is anything moving through its gravitational field, whether it is a spacecraft, a beam of light, or the very passage of time itself. This is the essence of Wheeler's elegant summary. Spacetime tells matter how to move, matter tells spacetime how to curve. It is a constant, mutual conversation between mass and the stage it sits upon. The deeper the curvature, the stronger the gravity, and the more dramatic the effects. And one of the most incredible effects is on time itself. In a strong gravitational field within one of these deep spacetime wells, time proceeds more slowly. It is as if the curvature creates a kind of resistance, a drag on the forward march of seconds. A clock at the bottom of the well ticks slower than a clock higher up on the slope. This is gravitational time dilation, and it is not a theory. It is a measured, verified fact of our universe. It means that time is not a universal metronome ticking at the same rate for everyone, everywhere. Your experience of time is deeply personal, intimately shaped by where you are and what gravitational landscape you are navigating. This single principle is the master key. It unlocks the bizarre behavior of time in every extreme region we are about to visit, from the crushing depths of a neutron star to the very edge of oblivion at a black hole. This ultimate point of no return is the event horizon of a black hole. Here, gravity is not just strong, it is absolute. The curvature of spacetime becomes so infinitely steep that the path leading away from the black hole closes in on itself. To escape, you would need to travel faster than light, and that is a rule even spacetime itself will not break. For a distant observer watching from a safe distance, this creates the most severe time dilation environment we can conceive. If you were to observe a spacecraft falling toward this boundary, you would witness something profoundly strange. the signals from its hull would stretch, shifting to longer, redder wavelengths. Its movements would become slower and slower and slower still, like a film gradually descending into a single frame. From your perspective, the craft would never actually cross the line. It would appear to fade, frozen for all eternity, a ghost ship forever stranded on the edge of darkness. This is the view from outside the gravity well, where time for the falling object seems to grind to a halt. But what of the astronaut inside that craft? Their experience is the starkest possible illustration of relativity's subjective truth. For them, time passes at its normal, familiar rate. The clock on their dashboard ticks forward, second by second. As they cross the event horizon, they would notice nothing special about that precise mathematical boundary. The universe outside would simply fall away behind them, while ahead lies the unknown heart of the black hole. One observer sees an eternity, the other experiences a moment. Both perspectives are equally true within their own frame of reference. This radical disconnect is not a paradox, but a fundamental feature of a universe where time is woven into the fabric of space. It forces us to ask what is real. Is it the frozen image we see from afar, or the continuous journey experienced within? Our current physics suggests both are valid, yet they tell two completely different stories about the same event. This extreme region challenges our deepest notions of information, reality, and the very limits of what our theories can describe. But what if you could approach that edge of oblivion and not fall in? This brings us to the second extreme region, the chaotic but stable orbits just outside a supermassive black hole. We are not talking about the small, stellar mass black holes, but the true giants, like Sagittarius, a star at the heart of our own Milky Way. These supermassive black holes possess a gravitational grip so powerful it can tear stars apart, yet their immense size creates a strange zone of possibility around them. Unlike the steep, fatal plunge near a smaller black hole, the gravity well of a supermassive one is so wide and deep that stable orbits can exist incredibly close to the event horizon. Here, time dilation is not infinite, but it is staggering. Imagine an astronaut in a specially shielded craft completing a single, harrowing orbit in this region. For them, the journey might take just a few hours, but for everyone else, for observers back on Earth or even in distant interstellar space, centuries would have marched by. This is not science fiction, but a direct prediction of the same physics that bends light and slows clocks. In fact, this extreme environment is our most powerful real-world laboratory for studying these effects. We cannot send a probe there yet, but the universe sends us signals. When astronomers point their telescopes at the chaotic maelstrom of matter swirling around Sagittarius A star, they are watching a natural experiment in extreme time dilation. The gas and dust screaming around that cosmic drain are subjected to such intense gravity that the light they emit is stretched to extraordinary degrees. This gravitational redshift is the direct, observable signature of time running desperately slow in that orbit. The light tells the story. It arrives at our telescopes tired, shifted far into the red because every wave, every photon had to fight its way out of that deep gravitational well. Each stretched wavelength is a testament to the seconds that were dragged out in that extreme place. By studying this light, scientists are not just watching a spectacle. They are testing the laws of physics under conditions of gravity so severe they are impossible to recreate anywhere in our solar system. They are learning how spacetime behaves when it is wound to its limit, and how matter conducts its final, furious dance before disappearing from our view forever. This environment teaches us about the dynamics of the universe's most powerful engines, and it all hinges on a simple, profound truth. Time is not a constant. It is a variable shaped by the landscape of the cosmos, and if orbiting a black hole can warp time to such a degree, what must be happening on the surface of something even denser? To find a place where time slows almost as dramatically as near a black hole, we must turn to the remnants of a stellar catastrophe. A neutron star is the collapsed core of a massive star that exploded in a supernova, a city-sized object containing more mass than our Sun. The gravity at its surface is so immense it creates the third extreme region where time itself is pulled into a deeper, slower rhythm. Picture the aftermath of that colossal explosion. What remains is a sphere only about 12 miles across, yet so incredibly dense that a single teaspoon of its material would weigh billions of tons. It is matter crushed to its absolute limit, where atoms themselves have been obliterated. Protons and electrons are forced together into a sea of neutrons, packed tighter than in an atomic nucleus. This unfathomable density warps spacetime into a profound well, second in depth only to that of a black hole. Standing on such a surface, if it were possible to survive the crushing gravity and intense radiation, you would witness a universe distorted by extreme physics. The sky above would not be a familiar dome of stars but a bizarre, lensed panorama. Light from distant stars struggling to climb out of this gravitational pit would be stretched and redshifted, their colors shifted toward the deep red. The entire cosmos would appear compressed into a circle directly overhead, a window to a universe where time is running faster. For a clock on that neutron star surface, time would pass about 20 to 30% slower than for a clock in the distant emptiness of interstellar space. This is not a trivial difference. Over a decade for an outside observer, only about 7 or 8 years would pass on that stellar surface. This measurable dilation is not just theoretical. We have cosmic lighthouses that prove it. Pulsars are rapidly spinning neutron stars that beam radiation like a lighthouse, and their incredibly regular pulses are the most precise clocks in the galaxy. Astronomers can detect the subtle effects of gravitational time dilation on these pulses, especially when the pulsar is part of a binary system, providing a natural laboratory to test Einstein's predictions under some of the most severe conditions possible. Studying these stellar corpses does more than confirm relativity, however. It allows us to probe the very nature of matter under pressures and densities that can never be recreated on Earth. By observing how light behaves and time warps near a neutron star, scientists gain insights into the strange state of ultra-dense nuclear material, a substance that may hold the key to understanding the fundamental forces that govern our universe. These objects are not just tombs for dead stars, they are beacons sending us encoded messages about the fabric of reality, written in the slowed ticks of time and the bent paths of light. The sheer density of a neutron star is almost beyond comprehension, yet there are places in the cosmos where the slowing of time is not caused by a single, monstrous object, but by the collective weight of an entire city of stars. To find the fourth extreme region, we must travel to the very heart of a galaxy. Picture our own solar neighborhood with vast, empty stretches between stars. Now journey inward toward the brilliant, crowded core of a giant elliptical galaxy like M87. Here, stars are not lonely specks of light. They are packed together millions of times more densely, a stellar metropolis where the night sky would be a perpetual, blinding daylight from the glow of countless nearby suns. This incredible concentration of mass, amplified by the unseen anchor of dark matter, creates a deep and wide gravitational well across the entire galactic core. The effect on time is subtle when compared to the violent drama at a black hole's edge, but it is profound and inescapable. Within this bustling nucleus, time runs measurably slower than in the galaxy's outer suburbs or in the lonely voids between galaxies. Think of it as a vast, shallow valley of spacetime, carved by the combined gravity of billions of suns. A clock placed in that core would tick just a tiny bit slower than an identical clock placed far out in the galactic countryside. Over a single human lifetime, the difference would be negligible, utterly impossible to notice. but the universe operates on timescales of billions of years. Over these cosmic epochs, that tiny difference accumulates. From the perspective of a hypothetical observer floating in intergalactic space, processes within that dense core would appear to unfold in slow motion. Stars might be born at a slightly slower rate, live their lives a little more leisurely, and meet their ends a touch later than identical stars in less crowded neighborhoods. This is not because the stars themselves are different, but because the very fabric of time in which their stories are written is stretched. This large-scale gravitational time dilation adds a fascinating layer to our understanding of cosmic evolution. It means that the universe does not have a single, synchronized clock. The aging of stars, the timing of galactic events, even the rate at which a galaxy's core evolves, can be influenced by the gravitational landscape it sits within. When astronomers look at the ancient, dense hearts of the universe's largest galaxies, they are not just looking back in time due to the finite speed of light. They are also peering into regions where time itself has flowed at a slightly more patient pace for billions of years. It is a gentle, universe-wide demonstration of a principle we first saw in its most extreme form. Mass tells spacetime how to curve, and that curvature, whether from a single neutron star or a billion suns, dictates the rhythm of time itself. The universe whispers its secrets through numbers, and the slowing of time is no exception. While the analogies of trampolines and deep wells help us visualize the warping of spacetime, there exists a precise mathematical key that unlocks the exact rate of this cosmic slowdown. It is an equation of breathtaking elegance and power, one that transforms a philosophical wonder into a calculable fact of nature. This is the gravitational time dilation formula. It may look intimidating at first glance, but its beauty lies in how directly it connects cause to effect. The formula states that the time interval measured by a distant observer, which we can call t, is equal to the proper time interval experienced near the mass, t0, divided by the square root of 1 minus 2 times the gravitational constant times the mass, all divided by the distance from the center times the speed of light squared. Let us break down what each of these symbols truly means. T is time as we would measure it, safe and far away. T0 is time for the brave soul or the resilient clock deep within the gravitational well. G is the universal gravitational constant, a fixed number that sets the strength of gravity's pull. M is the mass of the object creating the curvature, whether it is Earth, the Sun, or a black hole. R is your distance from the center of that mass, and C is the cosmic speed limit, the speed of light. The magic and the slowing of time happens inside that square root. The term 2gm over rc squared is the engine of the phenomenon. It is a ratio that compares the strength of the gravitational pull at your location to the fundamental energy scale set by the speed of light. As this ratio gets larger, the square root gets smaller, and since t0 is divided by this shrinking number, the time t measured from afar becomes larger and larger. This is the mathematics of a stretched second. When the mass m is huge or the distance r is very small, that critical ratio creeps closer to the number 1. As it does, the denominator of our fraction approaches 0. Dividing by a number near 0 yields an enormous result. In practical terms, this means that for a distant observer, a single tick of a clock near an immense mass can seem to stretch out toward eternity. We can breathe life into this abstraction with real numbers. For the relatively gentle gravity of Earth, the time dilation effect is minuscule but measurable. A clock at sea level will lag behind a clock on a mountain peak by about 3 microseconds over a year. For the vastly more massive Sun, the effect is stronger. A clock on its surface would tick about 66 parts per million slower than a clock far out in space. But it is when we apply the formula to a neutron star that the numbers become truly arresting. For a typical neutron star, that critical ratio inside the square root grows to about 0.2. Plugging that in, we find that time on its surface flows at about 80% of the rate it does in deep space. Over a decade out here, only 8 years pass there. This is no tiny microsecond adjustment. This is a profound rewriting of temporal experience, predicted precisely by a handful of symbols on a page. This formula is more than a calculator. It is a passport. It empowers us to compute the flow of time anywhere we can imagine, from the cloud tops of Jupiter to the brink of a supermassive black hole. It demystifies the cosmos, showing us that the seemingly magical slowing of time is not magic at all. It is a dependable, predictable feature of a universe where space and time are woven together into a single, flexible fabric. The equation takes the grand, sweeping concept of warped spacetime and gives us the tools to measure its every curve and contour. With it, we have moved from wondering to knowing. The mathematics is elegant, but the real question is more direct. How do we know this is not just a beautiful theory scribbled on a chalkboard? The proof is not found in distant galaxies, but in the precise ticking of clocks right here on Earth and in the satellites orbiting high above us. Our first great experimental confirmation came from a daring test conducted in the skies. In 1971, physicists Joseph Hafele and Richard Keating performed an experiment that now sounds like the premise of a science fiction novel. They took 4 incredibly accurate atomic clocks, placed them on commercial jetliners, and flew them around the world, once eastward and once westward. Then they compared them to identical clocks that had remained stationary at the United States Naval Observatory. The results were a triumph for Einstein's vision of reality. The clocks that traveled eastward, moving against the rotation of the Earth, indeed showed a measurable time difference when they returned. They were slightly behind the stationary clocks. This was not a malfunction. It was the combined signature of 2 relativistic effects. The high speed of the jets caused a slowdown from special relativity, while the change in altitude and the Earth's rotation influenced the clocks through the gravitational effects of general relativity. The numbers were tiny, mere fractions of a second, but they matched the predictions with stunning accuracy. For the first time, time dilation was not a theoretical curiosity. It was a measured fact captured in a metal suitcase flying on a Pan Am flight. Today, you carry the proof of this phenomenon in your pocket or your car. The entire global positioning system is a monumental, ongoing experiment in relativistic physics. Each GPS satellite orbits about 12,000 miles above the Earth. At that altitude, Earth's gravity is significantly weaker, which, according to general relativity, makes the satellite's atomic clocks run faster. Simultaneously, the satellites are moving at about 8,700 miles per hour, which, according to special relativity, makes their clocks run slower. These 2 effects do not cancel out. The gravitational effect is stronger. The net result is that the clocks on the satellites gain about 38 microseconds every single day compared to identical clocks on the ground. This might sound insignificant, but in the world of precise navigation, it is catastrophic. Light, and therefore the radio signals from the satellites, travels about 186,000 miles per second. In just 38 microseconds, light travels over 7 miles. If the engineers who designed the GPS system did not deliberately program the satellite clocks to tick slower before launch, to compensate for this predicted relativistic speed up, the entire system would become useless within minutes. Your map application would place you in the wrong city or the wrong country. Every time you ask for directions, every time a ship navigates a storm, every time a farmer guides a tractor with precision, you are witnessing a silent, continuous validation of Einstein's theories. These technologies are not just tools, they are constant, undeniable testaments to the malleable nature of time itself, proving the universe operates by these strange rules with every single navigation request. The cosmos bends time, and we have learned to build our world upon that bend. Light itself becomes a messenger, carrying the story of time's passage across the cosmic distances. When a photon, a particle of light, is emitted from the surface of a star or near a black hole, it must climb out of that deep gravitational well. This climb costs it energy. Since a photon's energy is tied directly to its color, losing energy means its wavelength stretches, shifting its color toward the red end of the spectrum. This phenomenon is called gravitational redshift, and it is the direct, observable fingerprint of gravitational time dilation. The very light that allows us to see these distant objects is also telling us, in its altered color, how slowly time was flowing at its point of origin. The deeper the gravity well, the greater the redshift. It is a cosmic postmark stamped on every beam of light that escapes an extreme region. We did not need to travel to a star to find this proof. In a landmark experiment at Harvard University in 1960, physicists Robert Pound and Rebka sought to measure this subtle effect right here on Earth. They used a brilliant method involving gamma rays emitted from a sample of radioactive iron. They placed a source at the bottom of a tower and a detector at the top, a vertical separation of just 22.5 meters. According to Einstein's theory, the gamma rays climbing upward against Earth's gravity should redshift by a minuscule amount, losing a tiny fraction of their energy. The predicted shift was almost impossibly small, but Pound and Rebka devised a way to detect it by using the resonant absorption of the gamma rays. Their results were a perfect match. They had measured the warping of spacetime over a distance shorter than a basketball court, confirming that light itself bears the weight of gravity's grip. In the vastness of space, this effect is written across the heavens in bold strokes. Consider a white dwarf, the Earth-sized ember of a sun-like star. Its intense surface gravity produces a noticeable gravitational redshift. When astronomers analyze its light, they find its characteristic spectral lines shifted redward, a clear signature of time moving slower on that dense surface. The effect is magnified 1,000-fold on a neutron star. Light struggling to escape that unimaginable density is stretched so dramatically that it provides one of our strongest confirmations of these objects' extreme nature. But perhaps the most compelling observation comes from the heart of our own galaxy. For decades, astronomers have meticulously tracked the motions of stars whirling around the invisible monster we call Sagittarius A star. By analyzing not just their orbits but also the light from these stars, scientists perform a double verification. They measure the star's incredible speeds, which indicate a tremendous central mass. And then they examine the starlight itself. The light from these stars, especially when they make their closest, most perilous approach to the black hole, shows a powerful gravitational redshift. This is not a Doppler shift from motion, but a distinct stretching caused by the star's light escaping the black hole's fierce gravity well during that moment. By mapping this redshift, astronomers have literally painted a picture of the warped spacetime in our galactic center. The light serves as a probe, telling us not just that a supermassive black hole is there, but how its gravity distorts the very fabric of reality around it. Thus, every telescope is also a time detective. When we peer into the cosmos, we are not just seeing objects as they were in the past due to the finite speed of light. We are also reading the personal history of time in those locations. The redshift of light from a distant quasar, a white dwarf, or a star at the galactic center is a direct report on the gravitational conditions and therefore the flow of time at its source. Light does more than illuminate. It narrates. It carries a coded message about the temporal landscape from which it came, allowing us to decode the universe's most profound secret. Time is not a universal constant but a local experience, and its story is written in the color of starlight. That same warping of light gives us a clear window into a gentler, yet profound, extreme region. Between the familiar gravity of our Sun and the crushing intensity of a neutron star lies a cosmic middle ground, the White Dwarf. This is the fate awaiting stars like our own, a preview of the extreme dilation to come. When a Sun-like star exhausts its nuclear fuel, its outer layers drift away in a beautiful planetary nebula, leaving behind its hot, dense core exposed. What remains is an object with the mass of our Sun, compressed into a sphere roughly the size of Earth. The material in a white dwarf is so compact that a single sugar cube-sized piece would weigh as much as an elephant here on our planet. This incredible density creates a gravitational field about 100,000 times stronger than Earth's, warping spacetime into a significant, though not catastrophic, well. On the surface of a white dwarf, time does slow down, but the effect is modest by cosmic standards. The dilation amounts to just a few parts per million slower than time in the distant void. Over a human lifetime, the difference would be utterly imperceptible, a matter of seconds. Yet for physicists, this precise, measurable shift is a golden opportunity. White dwarfs serve as a crucial intermediate laboratory. They exist in a gravitational regime far stronger than anything in our solar system, yet less violently extreme than a neutron star or black hole. This makes them perfect for testing and refining the predictions of general relativity. By studying the light from their incredibly dense, hot atmospheres, astronomers can detect the subtle gravitational redshift imprinted on their spectral lines. The amount of that redshift matches Einstein's equations with stunning precision, providing a clean confirmation of time dilation in a stable, observable environment. These stellar embers are more than just in points. They are stepping stones. Understanding the physics of a white dwarf, how matter behaves under that immense pressure, and how spacetime curves around it, directly informs our models of what happens when conditions become even more severe. They teach us about the equation of state of degenerate matter, a fundamental rulebook for how particles pack together when atoms are destroyed. This knowledge is essential for predicting the behavior of their denser cousins, the neutron stars. So, while a white dwarf's surface may not stretch seconds into years, it offers something equally valuable, a clear, calibrated benchmark. It shows us the continuum of gravity's influence, proving that the same principles that gently slow a clock on Earth also govern the final, faded glow of a once brilliant sun. In their quiet persistence, white dwarfs whisper the early chapters of a story that culminates in the silent fury of a black hole. But the ultimate extreme is not a surface or an orbit. It lies at the very end of the journey, a place our current laws of physics cannot fully describe. According to classical general relativity, at the absolute center of a black hole, all the collapsed mass is compressed into a single point of infinite density. This is the singularity. Here, the mathematics of Einstein's theory reaches its breaking point. The equations predict that the curvature of spacetime becomes infinite, and with it, the gravitational time dilation would also become infinite. In this theoretical model, time, as we know it, would simply stop. A clock falling toward this point would, from an outside perspective, have its ticking stretched to an eternal standstill. The singularity represents the ultimate frontier of our understanding and its greatest mystery. It is not a place in any conventional sense, but a boundary beyond which our concepts of space, time, and matter lose all meaning. The very existence of this prediction is a powerful signal. It tells us that general relativity, for all its brilliance, is an incomplete picture of reality. It beautifully describes the warping of spacetime on large scales, but it cannot handle the quantum-scale frenzy that must occur when an entire star's worth of mass is crushed into a volume smaller than an atom. To truly know what happens at that final point, we need a theory that unifies the cosmic rules of gravity with the probabilistic, fuzzy rules of the quantum world. This sought-after framework is called quantum gravity. It is the holy grail of modern physics, and the singularity is the question it must answer. So what truly happens there? Does time simply cease, frozen forever, or does it transform into something entirely new, a different dimension or state of existence our mathematics cannot yet capture? Some theories suggest the singularity might be a bridge to another universe, or a transition into a realm of pure quantum potential. Others propose that the intense quantum effects prevent the infinite collapse entirely, creating a dense, exotic core that rebounds or exists in a perpetual state of uncertainty. Confronting this theoretical limit does more than challenge our equations. It forces us to reconsider the most fundamental aspects of reality. We are compelled to ask if time and space are truly foundational, or if they are merely emergent properties of a deeper, more complex system that reveals itself only under such inconceivable strain. The journey from a mountaintop to a black hole's heart has shown us that time is fluid and personal. But at the singularity, we face the profound possibility that time itself might be a temporary construct, a useful story that the universe tells itself until the conditions become too extreme for the narrative to hold. This is where our exploration hits a wall of mystery, pointing toward a deeper truth still waiting to be discovered. A clock in motion tells a different story than one at rest. We have seen how gravity alone can stretch seconds, but the universe is a dynamic place, filled with whirling orbits and incredible velocities. To grasp the full picture of time in these extreme regions, we must introduce a second, equally powerful actor. Albert Einstein's earlier theory, special relativity, revealed that speed itself warps time. The faster you move through space, the slower your clock ticks relative to someone standing still. This is not a mechanical effect, but a fundamental feature of a universe where the speed of light is the ultimate constant. Now, imagine placing this high-speed clock deep within a powerful gravitational field, like the maelstrom surrounding a black hole. Here, the two great pillars of modern physics, general relativity and special relativity, join forces. The total slowing of time becomes a breathtakingly complex sum of two distinct effects. An object is both deep in a gravity well and moving at a tremendous fraction of light speed. The result is a compounded time dilation, a double distortion of the temporal landscape. We can witness this dramatic partnership in one of the most violent places imaginable, the accretion disk of a black hole. Picture a vast, superheated whirlpool of gas and dust, spiraling inward at velocities approaching half the speed of light. A single atom in this chaotic flow is subjected to an almost unimaginable physical ordeal. It is gripped by the black hole's immense gravity, which alone would slow its local time. Simultaneously, it is screaming along its orbital path at relativistic speed, which further slows its clock from the perspective of a distant observer. These two effects do not simply add together, they intertwine through the precise mathematics of relativity. For the innermost, fastest-moving material just outside the event horizon, time may pass hundreds or even thousands of times slower than it does for us. This extreme combined dilation is not a theoretical curiosity. It is written directly into the light, or rather, the high-energy radiation that these systems emit. The flickering, fluctuating X-ray signals we detect from black hole binaries are the direct signature of this superheated, time-dilated matter. The rapid flares and dips in brightness are generated in that frenzied disk, but by the time that information fights its way out of the deep gravitational well and reaches our telescopes, it has been stamped with the complex time signature of its origin. The patterns are stretched and distorted, a coded message about both the gravity of the whole and the velocity of the doomed material circling it. Astrophysicists spend careers decoding these signals. To build accurate models of a black hole's mass, spin, and environment, they must untangle this intricate knot of gravitational and kinematic time dilation. It is a monumental computational challenge, but a necessary one. Getting it wrong would mean misjudging the fundamental properties of some of the most energetic objects in the cosmos. This necessity underscores a profound and beautiful truth about our universe. Time is not shaped by a single force. It is a symphony conducted by two maestros, gravity and motion. Your personal experience of time's flow is the unique product of your position in spacetime's curves and your velocity along its contours. A stationary observer near a neutron star will age slower than someone far away purely from gravity. But if that observer begins to orbit the star at tremendous speed, their time will slow even further. This duality is everywhere, from the precise corrections in our GPS satellites, which must account for both their orbital speed and the weaker gravity at their altitude, to the ancient light from distant quasars. It reminds us that to truly understand the clocks of the cosmos, we must always ask two questions. Where are you, and how fast are you going? The answers together write the story of your time. The universe is not just curving space, it is stretching it. On the largest possible scale, a grander force comes into play, one that rewrites the rules of time across cosmic distances. This is the expansion of the universe itself, and it produces a phenomenon known as cosmological time dilation. It is a subtle but monumental effect, entirely separate from the gravitational warping near massive objects. Here, time's rhythm is tied not to local gravity, but to the history of space. When astronomers point their telescopes at a cataclysmic event in a galaxy billions of light years away, such as a supernova explosion, they witness something peculiar. The brilliant flash does not appear and vanish in an instant. Instead, the entire event seems to unfold in slow motion. The rise to peak brightness takes longer, and the fade back to darkness is more drawn out, compared to an identical supernova occurring in a nearby galaxy. This is not an illusion of distance. The light itself carries this stretched-out timeline. As the universe expands, the very fabric of space between galaxies stretches. Think of the light from that ancient supernova as a series of waves, like the crests of a wave on a rubber sheet. If you begin stretching that sheet while the waves are traveling across it, each wave crest gets farther apart. The wavelength stretches, which we see as a redshift, but crucially, the time between the arrival of successive wave crests also stretches. The ticking of the distant cosmic clock, encoded in the light's pulses, arrives at our telescopes slowed down. It is as if we are watching a film of the explosion projected onto an expanding screen, making every action appear more gradual and deliberate. This cosmological time dilation provides one of the most direct and elegant proofs that our universe is not static, but dynamically growing. By comparing the observed duration of distant supernova to the known physics of how such explosions should behave, scientists can measure the precise amount of stretching. This data does more than confirm expansion. It reveals the universe's changing tempo over billions of years. The amount of time dilation for an object depends directly on how much the universe has expanded since the light we see was emitted. This allows cosmologists to peer back into cosmic history and chart how the expansion rate has evolved, leading to the groundbreaking discovery that this expansion is accelerating, driven by the mysterious influence we call dark energy. In this grand view, time is not merely a passenger in the cosmos. Its flow is an active recorder of cosmic history. The slowed ticks we observe from the distant past are a direct echo of a younger, smaller universe. They tell us that time itself, on the largest scales, is a fluid dimension shaped by the overall geometry and destiny of all that exists. From the frozen edge of a black hole to the stretched light of a dying star at the edge of the observable universe, we find a unifying principle. Time is not absolute. It is a flexible, dynamic ingredient of reality, intimately responsive to both the local curvature of space and the global expansion of everything. These bizarre possibilities lead us to the most speculative frontier of all. Wormholes are theoretical shortcuts, tunnels through the folded fabric of spacetime itself. While they remain firmly in the realm of mathematics and science fiction, they offer a stunning thought experiment about the ultimate power of time dilation. Picture a stable, traversable wormhole as a cosmic subway with two entrances or mouths in distant parts of the universe. According to the equations, each mouth would be subject to the local gravitational conditions where it sits. If one mouth were placed near a powerful source of gravity, like a neutron star, and the other were left floating in the quiet emptiness of deep space, time would flow at dramatically different rates at each location. The mouth near the star would be a gateway into a slower time zone. Now consider a traveler. They step into the quiet, deep space mouth where time is normal. They pass through the tunnel and emerge moments later from the mouth anchored in the strong gravity well. From their perspective, the trip was brief. But because they exited a region where time is slowed, they might find that the universe outside that second mouth has aged years, decades, or even centuries during their short journey. In a more extreme setup, they could even emerge before they left, touching the edges of time travel itself. This is not magic, but a logical, if dizzying, extension of the gravitational time dilation we know is real. The wormhole simply provides a direct bridge between 2 points with vastly different temporal landscapes. The traveler experiences the differential flow of time not by waiting, but by changing their location in the gravitational field instantaneously. Such a scenario immediately confronts us with profound paradoxes. What if the traveler, after emerging in the past, could interact with their earlier self or prevent their own journey? These causality violations create logical knots that our current physics cannot untangle, suggesting that nature may forbid such shortcuts to preserve a consistent timeline. While traversable wormholes are almost certainly not possible with any technology or material we can conceive, they would require exotic matter with negative energy to hold them open. Their value is not in practicality. They are a stress test for our theories. By stretching the concept of time dilation to its absolute limit, they force us to confront the deepest questions about the structure of causality and the unity of space and time. They challenge the comforting idea of time as a universal river, always moving forward at the same rate for everyone. Instead, they paint a picture of time as a complex topographical map. Our universe may be a terrain of temporal mountains and valleys, where gravity creates high peaks of fast time and deep basins of slow time. Normally, we are stuck navigating the slopes, our personal time slowing as we descend into a gravity well. But the wormhole fantasy asks, what if you could tunnel directly from a valley to a peak? The journey through the tunnel might be short, but the difference in altitude, the difference in accumulated time, could be immense. This perspective transforms time from a sequence into a geography, a dimension that can be traversed not just through patience, but potentially through clever navigation of spacetime's contours. It is a reminder that the strange slowing of time near a black hole is not an isolated quirk. It is a clue pointing toward a far more intricate and interconnected cosmic reality, where the paths through space and the flow of time are threads in the same astonishing tapestry. A civilization born in a slow time valley would watch the cosmos age before its eyes. From their vantage point on a planet orbiting a neutron star or deep within a dense galactic core, the universe outside their gravitational well would appear to be a frenzied, accelerated spectacle. Stars in distant, less curved regions of space might flare to life and burn out in what seems like a few generations. Entire galaxies could merge and evolve within the span of their recorded history. Their night sky would be a theater of fast-forwarded cosmic drama, while their own world experienced time at a far more patient, drawn-out pace. This relativistic reality forces us to expand our definition of a habitable zone far beyond the simple need for liquid water and a stable climate. We must now consider the habitability of time itself. Could biology even begin under such a distorted clock? The building blocks of life rely on complex chemical reactions, the folding of proteins, the replication of molecules. If time is stretched by 20 or 30%, these fundamental processes would also operate in slow motion. Evolution, driven by random mutation and natural selection, would proceed at a comparably leisurely rate. A species on such a world might take millions of our years to achieve a change that required only hundreds of thousands of years on Earth. This raises a profound astrobiological question. Is there a universal tempo for life, a minimum speed at which chemistry must operate to become biology? Or is life infinitely adaptable, capable of finding a rhythm in any temporal landscape the universe provides? Imagine an intelligent species emerging under these conditions. Their entire perception of reality would be framed by this slow, deep time. Their philosophy might center on permanence and patience, seeing the frantic universe outside as a fleeting, ephemeral display. Technological progress could be unimaginably deliberate by our standards, with projects spanning epochs. Conversely, their astronomy would be astonishingly advanced, for they could observe cosmic events unfold in what felt like real time, watching the life cycles of stars with the ease we watch the changing seasons. This is not merely a flight of fancy. It is a necessary thought experiment that stretches our understanding of life's potential. When we scan the cosmos for signs of other civilizations, we often listen for signals or look for technological signatures that operate on human timescales. But a society whose very perception of time is rooted in a deep gravitational well might communicate or build in ways we cannot yet recognize, on schedules spanning centuries between simple greetings. Their concept of urgency, of history, of the future itself would be alien to us. The search for life must therefore become a search across multiple dimensions, not just of space but of spacetime. We are not just looking for planets in the right place, we are listening for whispers from the right time, or rather, from places where time itself flows to a different, slower beat. The most profound puzzles in physics arise where our two great theories collide. General relativity, governing the immense, meets quantum mechanics, ruling the infinitesimal. At the event horizon of a black hole, this collision creates a crisis known as the information paradox. From a distant vantage point, we see matter and its information frozen forever at that boundary, a final monument suspended in infinite time dilation. Yet, Stephen Hawking's revolutionary work showed that black holes are not truly eternal. Through subtle quantum effects at the horizon, they slowly leak energy, evaporating over astronomical timescales until they potentially vanish entirely. This presents an impossible contradiction. Quantum mechanics is built on a sacred principle: information, the specific arrangement of particles that made up a star, a spacecraft, or an astronaut, can never be truly destroyed. It can be scrambled beyond recognition, but the blueprint must persist in some form. Relativity, with its frozen image and final singularity, seems to erase that blueprint completely. So when the black hole evaporates, what happens to all that information? Does it simply cease to exist, violating a cornerstone of physics? Or is it somehow encoded in the Hawking radiation, a faint whisper of everything that fell in? This is not an abstract debate. The information paradox strikes at the very meaning of causality and reality. It suggests that our understanding of time in these extreme regions is fundamentally flawed. Perhaps time, as a smooth, flowing continuum, breaks down at the quantum level. Some of the most promising ideas for a solution come from holography, a radical concept suggesting that all the information contained within a volume of space, like the interior of a black hole, might be perfectly encoded on its bounding surface, its event horizon. In this view, the three-dimensional world we experience could be a projection from a two-dimensional surface where time and quantum information are interwoven in a new way. The frozen image we see from outside is not an illusion, but the real data stored like a cosmic hard drive. The evaporation process would then be a slow, complex decoding of that information back into radiation. Other theories propose that time itself is not a fundamental ingredient of the universe, but an emergent property that arises from the quantum entanglement of particles, like temperature emerging from the motion of molecules. In the chaotic quantum foam at a horizon, this emergent time might dissolve, allowing information to escape through pathways our current math cannot yet trace. Each proposed solution forces us to rethink the nature of reality in startling ways. Studying the infinite dilation at a black hole's edge, therefore, is far more than an astronomical pursuit. It is a direct experiment using the cosmos itself as a laboratory to probe the deepest laws of existence. The paradox is a beacon, guiding us toward a more complete theory of quantum gravity. It tells us that by staring into the place where time appears to stop, we might finally learn what time truly is. A brother and sister stand together on a quiet launch pad, their shared history written in matching smiles and familiar eyes. One boards a vessel built for a journey unlike any other, not to traverse great distances at impossible speed, but to dwell in a deep well of gravity. Their destination is a stable research orbit around a neutron star, a decade-long mission measured by the clock on the ship's console. The other remains here, feet planted firmly on the Earth, living a life that unfolds to the rhythm of our gentle world. This is not the classic twin paradox of rockets and acceleration. This is its gravitational cousin, and its consequences are even more starkly personal. When the ship returns, the reunion holds a silent, physical truth. The sibling who ventured into that extreme region of curved spacetime steps down from the craft, appearing noticeably younger than the one who stayed behind. For the astronaut, only 10 years have passed. They experience the full decade of research, of daily routines and personal reflection, all ticking away at the steady, familiar pace of their own heartbeat. But the sibling on Earth has lived through 12, perhaps 13 years in that same interval. Their face carries those extra years, their body has aged according to the faster ticking clock of our planet's weaker gravity. The profound difference lies not in a trick of perspective or a symmetry broken by a turn-around maneuver, as in the velocity-based paradox. It is rooted in the immutable geometry of spacetime itself. The two siblings occupied different gravitational potentials. One lived high on the shallow slope of Earth's gravity well. The other spent a decade much deeper in the steep, severe curvature surrounding the Neutron Star. Time itself flowed more slowly in that deeper well. Every biological process aboard that ship, from cellular repair to neural activity, operated at that slowed tempo. They did not feel it, for their local reality was perfectly consistent, but the cumulative effect when compared to the uninterrupted timeline of Earth is a tangible divergence in their very aging. This thought experiment moves the concept from the abstract realm of clocks and equations into the intimate space of human experience. It asks us to consider the personal history that would be written in those missing years. The Earth-bound sibling would have witnessed seasons the astronaut never saw, celebrated birthdays they did not share, and accumulated memories formed during a stretch of time that, for the traveler, simply did not exist in the same measure. Their shared past would now branch into two different personal futures, all because one of them lived where spacetime was more severely curved. Such a scenario forces a deeply personal question. Which timeline is the real one? The answer, relativity insists, is that both are equally real. Each individual's experience of time is valid and complete within their own frame of reference. There is no universal clock to declare one sibling's years more authentic than the other's. This is the heart of relativity's revolution. It tells us that our most personal measure, The aging of our bodies, the accumulation of our memories, is not a universal constant, but a personal journey through the evolving landscape of the cosmos. The flow of time is not something that happens to you. It is an experience woven from where you are and how you move. The clocks of the cosmos are about to speak with a new and startling clarity. Our ability to listen is advancing, with a new generation of observatories poised to turn gravitational time dilation from a fascinating prediction into a precise, everyday tool for cosmic exploration. Leading this charge is a mission that will listen not with light, but with gravity itself. The Laser Interferometer Space Antenna, known as LISA, is a revolutionary space-based observatory designed to detect the ripples in spacetime called gravitational waves. While current ground-based detectors have opened this new window, LISA will operate in the quiet of space, sensitive to lower frequency waves from the most massive systems in the universe. Its primary targets will be the final, fatal dances of compact objects. LISA will witness, for months or even years, the slow, inexorable inspiral of two neutron stars or black holes as they circle each other, losing energy and spiraling closer. This is where time dilation becomes a critical character in the story. As these massive objects whirl in their deep mutual gravity well, their orbital period speeds up. The intense time dilation in that region imprints itself on the gravitational wave signal LISA receives. By tracking the subtle changes in the frequency and phase of these waves with exquisite precision, scientists will be able to measure not just the masses and distances of these objects, but also map the severe warping of spacetime around them. The gravitational waves carry a direct record of how time itself was flowing in that extreme environment, allowing us to test the predictions of relativity in regimes of gravity we have never before been able to probe so directly. While LISA listens to the whispers of spacetime, a new class of ground-based optical telescopes will bring our vision into razor-sharp focus. Instruments like the 30-meter telescope represent a colossal leap in light-gathering power and resolution. With a primary mirror 30 meters across, it will collect far more light than any current telescope, allowing it to obtain exquisitely detailed spectra of incredibly faint objects. One of its most thrilling targets will be the stars whirling around Sagittarius A star at the heart of our galaxy. The TMT will not just see these stars as points of light, it will dissect their light with phenomenal detail. By analyzing the precise gravitational redshift in their starlight, especially during their closest approaches to the black hole, astronomers will be able to create a high-definition map of the spacetime curvature in that region. It will be like moving from a rough sketch to a finely surveyed topographic map of a gravitational mountain. This will allow for unprecedented tests of how matter and light behave in this extreme laboratory, potentially revealing subtle deviations that could hint at new physics beyond Einstein's theory. Together, these instruments represent a fundamental shift. Time dilation will no longer be a curious side effect we must account for. It will become a primary diagnostic tool, a direct probe we actively use to understand the most violent and energetic phenomena in the universe. The slowing of time, once a philosophical puzzle, is becoming a precise language. With these new ears and eyes, we are learning to listen to its stories and read its messages from the deepest wells of gravity, bringing the most extreme regions of our universe into a clarity we have only ever dreamed of. The equations of relativity find a powerful echo in the stories we tell ourselves. For decades, the haunting idea of time flowing at different rates has not been confined to physics journals, but has ignited the imaginations of filmmakers, novelists, and artists. They transform complex principles into visceral human experiences, allowing us to feel the weight of a slowed second in our bones. Perhaps the most famous modern exploration is the film Interstellar, where a crew visits a planet orbiting the supermassive black hole Gargantua. The intense gravity near this fictional world causes a single hour on its surface to equal 7 years back on their ship and across the universe. This is not just a plot device, it is a narrative engine that drives the entire story toward profound emotional consequences. The crew's desperate race against the planet's crushing waves becomes a race against a different kind of tide, the relentless, accelerated flow of time for everyone they have ever loved. When they return to their vessel, the captain has aged only hours, but he watches decades of video messages from his children, now grown without him. This scene crystallizes the human cost of relativity. It is not about clocks, but about connection, loss, and the unbearable stretching of a parent's promise across an uncrossable temporal divide. Such stories take creative license, of course, simplifying the terrifying astrophysics of a black hole's accretion disk into a watery landscape. Yet their power lies in this very translation. They make the abstract intimately personal. They ask us not to calculate the Lorentz factor, but to contemplate a simple, devastating question. What would you sacrifice, and who would you become if your hour was someone else's lifetime? This question resonates because it touches a universal anxiety about time itself, our shared but personal race against it. Science fiction has long used this concept as a lens to examine fate and memory. In stories where astronauts return from near-light-speed journeys to find Earth centuries advanced, we see explorations of loneliness and displacement. The traveler is a ghost in their own future, a living artifact in a world that has written them into history. These narratives grapple with the philosophical shock of relativity, that there is no now that encompasses the entire universe. Your present moment is yours alone, and if you move through space-time differently than those you love, your shared now can fracture forever. By dramatizing this fracture, artists perform a vital service. They spark a public curiosity that pure equations might not. A viewer leaving the theater after Interstellar is not just entertained, they are often driven to look up explanations, to watch documentaries, to wonder. They become participants in a larger conversation about the nature of reality. These cultural interpretations act as a bridge, transforming the extreme physics of black holes and neutron stars from distant curiosities into frameworks for exploring the most human of themes: love, regret, legacy, and our place in a cosmos far stranger than we ever supposed. They remind us that science does not rob the universe of wonder. It provides the foundation for our most profound stories, asking what it means to be human when the one constant we thought we could rely on, time itself, becomes a fluid and personal journey. The profound disconnect between two clocks forces a question that has echoed through the ages, long before we could measure it. Is time itself a real, flowing river, or is it merely an illusion, a useful story we tell to make sense of change? The stark evidence from black holes and neutron stars does not just challenge our clocks, it challenges our deepest intuition about the nature of reality. If the passage of time depends entirely on where you stand and how you move, can we truly say it is a fundamental ingredient of the universe, or is it something that emerges from a deeper, timeless structure? This question sits at the crossroads of physics and philosophy. For centuries, the human experience of time has been one of relentless flow, an irreversible march from a fixed past through a fleeting present into an uncertain future. This feels undeniably real, but relativity paints a different picture, one where your personal present is not the same as anyone else's if you are separated by gravity or motion. There is no universal now that sweeps across the cosmos. Your moment of reading this sentence and a star's explosion in a distant galaxy cannot be definitively ordered as past or present for all observers. This shatters the classical idea of a single, shared timeline. Some physicists and philosophers propose a model that accommodates this strange reality called the block universe. In this view, past, present, and future all exist equally, laid out like frames in a film. What we perceive as the flow of time is merely our consciousness moving through this static structure, like a spotlight scanning across a vast, finished landscape. The astronaut and the Earth-bound sibling both exist in their younger and older states within the block. Their reunion is not a creation of a new moment, but simply our awareness arriving at that predetermined point in the four-dimensional landscape. From this perspective, time dilation is not about slowing a flow, but about the different angles at which different observers slice through the block. This idea is deeply counterintuitive. It suggests that the future is already written, that free will might be an artifact of our limited perspective within the block. It feels cold, deterministic, and at odds with everything we feel. Yet it emerges naturally from the mathematics of relativity, which treats time as a dimension much like space, woven into a single, unchanging spacetime fabric. The intense warping near a black hole is not warping a river, but twisting this fabric itself. Our powerful, subjective experience of a flowing present, however, cannot be dismissed. Neuroscience tells us this feeling is central to consciousness, a narrative constructed by our brains from a cascade of sensory inputs, so we are left with a profound duality. Objectively, the laws of physics suggest a universe where time as a flowing entity might be an illusion. Subjectively, our lived experience of duration, memory, and anticipation is the very foundation of meaning and identity. The extreme regions of space do not resolve this tension. Instead, they amplify it, showing us that the universe's architecture is fundamentally incompatible with our innate feeling of a universal now. This leaves us not with a simple answer, but with a richer, more humbling understanding. Time may not be what we think it is. The steady tick we rely on is a local phenomenon, a personal rhythm dictated by our modest place in a gentle gravity well. Venture into the cosmos's severe landscapes, and that rhythm stretches and distorts, revealing a deeper truth. Our reality is not a stage upon which time passes. We are participants in a dynamic, interactive fabric where what we call time is a relationship, a measure of change and connection between events, entirely dependent on our path through the cosmos. The flow we feel may be the story our minds tell as we journey through that immense and finished tapestry. Our search for time's true nature has gifted us with the power to measure its every whisper. The relentless drive to understand its flow in the cosmos has not just answered questions, it has revolutionized the very art of measurement here on Earth. The most profound legacy of gravitational time dilation may be the clocks it forced us to build. To detect the subtle warping predicted by Einstein, we needed instruments of almost unimaginable precision. That need became the mother of invention, pushing timekeeping technology into a realm that borders on science fiction. Today's most advanced atomic clocks bear little resemblance to the cesium beam devices of the past. They are miracles of quantum engineering, often using single atoms suspended in intricate webs of laser light, within traps so still and cold that the atom's natural vibrations can be measured with staggering accuracy. These optical lattice or ion trap clocks are so sensitive they do not just confirm time dilation, they feel its gentlest touch. A modern optical clock can detect the difference in time's flow between two shelves on a bookcase. Raise such a clock by a single centimeter, moving it slightly farther from Earth's center of mass, and its exquisite mechanism will register the infinitesimal speed up. This is not a theoretical limit, it is a routine demonstration in laboratories around the world. We are now measuring gravitational effects on a human scale, watching time itself bend across the height of a coffee mug. But these devices are far more than laboratory trophies. They have become our most powerful tools for asking fundamental questions about the stability of reality itself. By comparing clocks made of different elements or clocks kept in different states, scientists can search for tiny variations in the so-called fundamental constants of nature. These are numbers like the fine structure constant, which governs the strength of electromagnetic interactions. Is this number truly constant across all of time and space, or does it drift imperceptibly? An optical clock is a detector for such cosmic shifts, a canary in the coal mine of physics. If the constants waver, the clock's tick will change. Furthermore, these networks of ultra-precise clocks are forming a global web that can sense the universe's faintest tremors. Just as Lisa will listen for gravitational waves in space, a future network of Earth-based optical clocks could detect the subtle compression and stretching of spacetime caused by passing low-frequency gravitational waves from supermassive black hole mergers. Each clock would act as a single, unbelievably sensitive node in a planet-sized detector. This pursuit is also leading to a redefinition of the second itself, the fundamental unit of time in our scientific and daily lives. For decades, the second has been defined by the microwave vibrations of the cesium atom, but optical clocks, with their far higher ticking frequencies, are over 100 times more precise and stable. The global scientific community is now in the final stages of transitioning to a new standard based on optical transitions, a change that will ripple through navigation, communications, and fundamental research. It is a beautiful, circular journey, the quest to understand how time bends near a black hole, born from pure curiosity about the universe's extremes, has compelled us to master time here on Earth with a precision our ancestors could not have dreamed of. We sought to map the valleys of spacetime out there, and in doing so, we learned to survey its most minute contours right here. This is the hidden engine of discovery, where the drive to answer a profound why unlocks a world of practical how, gifting us not just deeper understanding, but new eyes to see the universe with. Even our own star, the steady heart of our solar system, bends the fabric of time. The sun's immense mass, nearly all the matter in our cosmic neighborhood, creates a gentle but definitive dip in spacetime. On its searing surface, time flows about 66 parts per million slower than it would in the empty space far beyond Pluto's orbit. To grasp that scale, think of a clock placed on the sun. Over an entire year, it would fall behind a distant clock by roughly 21 seconds. This is a subtle effect, yet it is precisely measurable, and it matters profoundly for our exploration. Consider the Parker Solar Probe, humanity's first mission to touch the sun. As this spacecraft makes its daring close passes, diving through the star's outer atmosphere, it is not just battling incredible heat. It is navigating a region where spacetime itself is curved. The probe's onboard systems, its communications, and the timing of every scientific measurement must account for this gravitational time dilation. If engineers did not correct for it, the probe's navigation data would slowly drift, its position calculations would become inaccurate, and its priceless observations could be misaligned. This is not a theoretical exercise. It is essential engineering, proving that relativity is baked into the practical reality of spaceflight. The sun's gravity manifests in another, beautiful way predicted by Einstein. During a total solar eclipse, when the moon perfectly blocks the sun's blinding face, astronomers can see the stars in the background sky. In 1919, observations during an eclipse showed that the sun's gravity was bending the light from those distant stars, making them appear slightly out of position. This was the first great experimental triumph for general relativity. That bending of light and the slowing of time are two sides of the same coin, both stemming from the curvature of spacetime. The sun acts as a perfect nearby laboratory. Its gravity is strong enough to produce clear, detectable effects, yet it is stable and predictable. By studying how light and time behave in its presence, we calibrate our models and confirm our equations with exquisite precision. This gives us immense confidence. When we then point our telescopes at a black hole a billion light-years away and see its light bent and reddened 1,000 times more severely, we are not guessing. We are applying a rulebook we have already verified in our own celestial backyard. Our home star is more than a source of light and life. It is a teacher offering a gentle, introductory lesson in the warping of the cosmos, preparing us to comprehend the far more violent classrooms that lie in the deep dark. Deep within the halo of our galaxy drift ancient cities of stars. Globular clusters are dense, spherical swarms containing hundreds of thousands, sometimes millions, of stars bound together by their mutual gravity. They are relics from the galaxy's youth, and their serene glow hides a subtle, collective influence on time itself. While no single star in a cluster rivals the gravity of a neutron star, their sheer numbers create a significant, shared gravitational potential. In the crowded core of such a cluster, the combined pull of all those suns carves a gentle but wide basin in spacetime. Here, time does not crawl as it does near a black hole, but it does adopt a more patient rhythm. Stars born and living in that dense core experience time, flowing slightly slower than identical stars out in the sparse galactic field, or even compared to their cluster siblings orbiting in the more spacious outskirts. The effect is minute, perhaps altering the passage of time by mere fractions of a percent. Yet over the billions of years these clusters have existed, that tiny differential accumulates. It means the nuclear furnaces in those core stars burn at a very subtly reduced rate from our distant perspective. Their evolution, their journey from birth to final rest, unfolds in a fractionally stretched out timeline. This presents a fascinating correction for astronomers. Globular clusters are among the most important cosmic clocks we have. By studying the oldest, coolest stars in a cluster, scientists can estimate its age, which in turn helps date the universe itself. But if the stars in the dense core are living in a slightly slower time zone, their apparent age could be a subtle misdirection. Their light and their chemistry tell a story that has been narrating itself in a slowed-down voice. To get the timing exactly right, to truly understand the life cycles of these ancient stellar populations, researchers must now account for this collective relativistic drag. It is a whisper of Einstein's theory in the most ancient neighborhoods of our galaxy, reminding us that even in the seemingly quiet, stable realms of the cosmos, time is never truly absolute. It is a fluid dimension shaped by the collective weight of everything around it. This unseen mass weaves the deepest gravitational valleys in the cosmos. Dark matter, the universe's ghostly scaffolding, exerts a profound, if gentle, influence on the flow of time itself. It does not clump into dense stars or black holes, but spreads in vast, diffuse halos that envelop entire galaxies. This immense but thinly distributed mass creates the broadest and most pervasive gravitational wells in the universe. Within the halo of our own Milky Way, the collective pull of this invisible substance subtly slows the passage of time compared to the great voids between galaxies. The effect is incredibly faint, a whisper compared to the shout near a neutron star. Yet it is everywhere, a background hum of temporal drag woven into the fabric of cosmic structure. Because dark matter makes up over 80% of a galaxy's total mass, it is the primary architect of this large-scale gravitational landscape. The stars and gas we see are merely bright ornaments on this invisible framework. This means that to truly understand how time flows across a galaxy, we must account for the gravity we cannot see. The rotation curves of spiral galaxies provided the first clue to dark matter's presence, showing stars orbiting far too quickly for the visible mass to hold them. Now we consider a more subtle signature. In theory, a perfectly precise map of gravitational time dilation across a galaxy would not follow the distribution of its glittering stars. Instead, it would trace the contours of its dark matter halo. Where the dilation is slightly stronger, the unseen mass is slightly more concentrated. This presents a breathtaking future possibility. By one day measuring the minuscule variations in time's flow across vast distances, we could chart the invisible geography of the cosmos. It turns time itself into a probe, a cosmic divining rod for the universe's greatest mystery. Such a map remains far beyond our current technical reach, requiring a network of clocks with a sensitivity we can scarcely conceive, distributed across interstellar space. Yet the principle is sound, grounded in the same equations that govern clocks on mountains and satellites in orbit. It reframes our quest to understand dark matter. We are not just searching for a missing particle, we are learning to read its signature in the most fundamental rhythm of all, the steady but variable ticking of the universe's clock. Each extreme region we have visited, from the frozen edge of a black hole to the patient core of a star cluster, reveals time as a flexible dimension. Dark matter teaches us that this flexibility extends to the grandest scales, that the unseen majority of the cosmos is quietly, constantly, bending the very thread of time. That bowling ball on the trampoline is more than a visual aid, it is a bridge to understanding. The fabric sags under the weight, creating a curved slope. Now picture placing two identical, simple battery-operated clocks on that surface. One rests far out on the flat, taut edge. The other is carefully set down deep in the curved dip, right next to the heavy ball. This simple setup holds the key to visualizing the impossible. In our analogy, the clock in the deep dip will tick more slowly than its twin on the flat. Why? Think of its internal mechanisms, the tiny gears or quartz crystal vibrations that mark each second. In our metaphorical world, those mechanisms must operate against the steep, curved slope of the fabric. It is as if each tick requires more effort, more work, to climb that local hill and register the passage of a moment. The clock on the flat edge has no such struggle. Its ticks flow freely and quickly. This is a direct, intuitive parallel to gravitational time dilation. A massive object like a star or planet warps spacetime, creating a gravitational well. A clock placed in that well at the bottom of that slope does not tick slower because its gears are strained, but because time itself is stretched by the curvature. The work the metaphorical clock does is analogous to the struggle of light or information, or the very progression of events, trying to make its way through that severely warped region. When a beam of light escapes from the surface of a dense star, it loses energy, its wavelength stretching to the red, just as our imaginary clock's ticks are stretched apart. The analogy is not perfect, of course. Spacetime is a four-dimensional fabric, not a two-dimensional sheet, and gravity is not a force pulling things down into a dip, but the curvature itself. Yet, this visualization succeeds because it gives our minds something to hold onto. It translates an abstract mathematical field, described by tensors and equations, into a physical model we can almost feel. We can picture the slope, we can sense the difference in effort. That mental picture allows the true strangeness to settle in. It helps us accept that if we were to stand beside that clock in the dip, our own biological processes, our thoughts, our aging, would all proceed at that same slowed rate relative to someone on the flat. We would feel normal, but the universe outside our well would be a frenzied blur. By anchoring the mind bending to the tactile, the trampoline model turns a cosmic mystery into a conceivable, if profound, feature of reality. It reminds us that the universe operates on geometry, and in that geometry, the steepness of a curve dictates the rhythm of time. A black hole's edge holds more than a frozen moment, it holds a library. From our distant vantage point, the final fate of anything crossing that threshold is not destruction, but preservation in an almost magical state. As an object approaches, its image stretches and reddens, its last signals slowing to an eternal whisper. To our eyes, its entire history of infall is not erased, but meticulously smeared across the surface of the event horizon, like a final, timeless photograph being developed over infinite eons. This bizarre encoding is not science fiction, but a serious implication of our best physics, a concept that links the warping of time directly to the nature of information itself. It suggests that within these regions of extreme time dilation, the universe is not losing memories, but writing them onto the most durable medium imaginable, the very boundary of oblivion. This idea finds a home in a radical theory called the Holographic Principle. In this view, all the information needed to describe a three-dimensional volume of space, like the interior of a black hole, can be perfectly encoded on its two-dimensional surface, its event horizon. Think of a security hologram on a credit card. The flat, shiny sticker contains all the data to project a three-dimensional image. In a similar, though vastly more complex way, the scrambled, stretched data of every star, gas cloud, and hypothetical spacecraft that ever fell in could be written onto the black hole's spherical surface. The infinite time dilation we see from outside is the mechanism of this writing. Because an object's final moments are stretched across forever, its information is not dropped into a pit, but carefully painted, bit by bit, onto the horizon's fabric. This transforms a black hole from a cosmic shredder into the universe's ultimate time capsule. It becomes a celestial archive, preserving a complete, if utterly scrambled, record of its own formation and everything it has ever consumed. The key to unlocking this archive, however, remains one of physics' greatest quests. If the information is truly there, how is it stored? Is it in the precise arrangement of spacetime itself at the boundary, in some quantum structure we cannot yet perceive? And if it is preserved, how could it ever be retrieved, especially if the black hole eventually evaporates through Hawking radiation? These questions strike at the heart of our understanding of reality, because they tie the flow of time directly to the concepts of entropy and information. Entropy is a measure of disorder, and it always increases. A black hole, with its immense gravity and simple description by just mass, spin, and charge, appears to be a state of maximum entropy. Yet, if it contains the complex information of everything inside it, that entropy is not lost, just hidden in a form we cannot read. The quest to understand this is the quest to understand how the universe keeps its books. It implies that in the places where time slows to a halt, we might find the rules for how all information, all history, is fundamentally recorded and maintained. The slowing of time is not just a curious side effect of gravity. It could be the universe's method of ultimate data storage, a way to ensure that not a single bit of its story is ever truly lost, only transformed and waiting for a reader with the right key. The ultimate journey would not be measured in light years, but in the passage of time itself. For a civilization that could navigate the deepest gravity wells, the cosmos would offer a path not just through space, but through the epochs. Imagine a vessel not merely moving at great speed, but deliberately plunging into a carefully calculated orbit around a stable, supermassive black hole. The crew's objective is not to explore the hole itself, but to use the severe spacetime curvature as a temporal engine. For them, a single, stable orbit lasting perhaps a year of ship time could see a millennium or more unfold in the galaxy beyond. They could, in principle, launch toward a distant star, swing around this relativistic anchor to let external time accelerate, and emerge from the maneuver to find their destination star system aged and changed, its civilizations risen and fallen, all within a single human lifetime aboard the ship. This is the speculative pinnacle of harnessing time dilation, turning a natural phenomenon into a tool for crossing not just distance but time. The practical barriers are, of course, staggering. The energy required to reach such a region and achieve a stable orbit is unimaginable. The radiation and tidal forces near any black hole capable of producing such extreme dilation would vaporize any known material. And the navigation precision needed is far beyond our current conception of physics and engineering. Yet, the thought experiment is not worthless. It stretches our understanding of what might be possible within the laws of physics as we know them. It forces us to consider time as a dimension that might one day be navigated with intention, not just endured. The ethical questions alone are profound. What would it mean to step out of the mainstream flow of cosmic time? A crew undertaking such a journey would become temporal pilgrims, leaving behind everyone and everything they knew, not by traveling far away, but by stepping aside from the shared rhythm of history. They would return as living artifacts from a forgotten era, observers in a future that had grown without them. Their knowledge, their culture, their very biology would be relics. Could such a journey ever be justified? The speculation pushes far beyond engineering into the realm of philosophy and human purpose. It asks whether our destiny is to simply experience time's flow or to one day learn to steer it. This vision of a far future capability, born from today's study of black holes and neutron stars, highlights a beautiful truth about pure science. The drive to understand the most extreme corners of the universe, to map the warping of spacetime around a distant singularity, is not just an academic exercise. It is the act of reading the universe's deepest operating manual. Every equation tested, every gravitational wave detected, every redshift measured is a sentence decoded. And within that manual, we find not just descriptions of what is, but hints of what could be. The principles that freeze a clock at the event horizon are the same principles that might, in a universe of unfathomable advancement, allow for a conscious choice to slow one's own time. By mastering the extremes, we are not just learning about the cosmos. We are exploring the full palette of possibilities within reality's laws, sketching the first, faint outlines of capabilities that could one day transform our species' relationship with the universe itself. The journey from curiosity to capability begins by staring into the abyss and daring to understand its clock. Our voyage has revealed a cosmos where time is not a universal river, but a personal path. From the subtle tick of a mountain clock to the frozen image at a black hole's edge, we have traced gravity's hand as it sculpts the very rhythm of reality. This is not abstract theory, it is the operating system of our universe, written into the light from distant stars and engineered into the satellites guiding our daily lives. Each extreme region, from the crushing surface of a neutron star to the silent archive of an event horizon, teaches us the same profound lesson. Your now is not my now. Your second is not my second. Time is a dialogue between matter and the stage it occupies, a flexible dimension that breathes with the curvature of space. This understanding reshapes everything. It transforms black holes from mere destroyers into cosmic laboratories and timekeepers. It pushes our technology to build clocks so precise they feel the gravity of a bookshelf. It forces our physics to confront the information paradox, guiding us toward a deeper theory of quantum gravity that may one day unite the very large with the very small. And yes, it lives in your pocket. Every time your phone pinpoints your location on a map, it is silently consulting the corrected ticks of atomic clocks in orbit, clocks that must obey Einstein's rules to keep our world connected. That mundane act is a quiet testament to a magnificent truth. The universe is far stranger, more interconnected, and more wonderfully bizarre than our everyday senses suggest. We have journeyed to places where seconds stretch into eons, and in doing so, we have found a new perspective on our own place within the cosmic story. The flow of time is a gift of your position in the grand tapestry, a personal journey through an immense and finished landscape. Let this exploration be a reminder to look up and wonder. The night sky is not just a collection of distant lights, it is a map of countless different times, all flowing at their own unique pace, waiting for us to learn their stories.